Welcome to Lecture 6.3, Normal Linear Maps. When we studied Jordan canonical form in the section on spectral theory, we proved the following curious result that we call corollary 4.14. If A and B are commuting diagonalizable linear maps, commuting means AB equals BA, then they are simultaneously diagonalizable. That is, for some invertible linear map P, we can conjugate both A and B by P to get a diagonal matrix. So D sub A is P inverse AP, and D sub B equals P inverse BP. So purely algebraically, just looking at this statement, this might be a cute result, but it's not in any way clear what good it is or what it's really saying. And that's because the real meat behind this is in the geometry. It's understanding how P represents a change of basis matrix. So let's translate this statement into geometric terms. So anytime we have a matrix that's diagonalizable, like these, then the diagonal matrix consists of the eigenvalues. And A and B clearly don't have to have the same eigenvalues. But P is the change of basis matrix that consists of the eigenvectors along the columns. So what this is really saying is that if we have two linear maps that commute and they have a basis of eigenvectors, then we can find a common basis of eigenvectors. In other words, a basis that are eigenvectors of both A and B. Now, it's not saying that any basis of eigenvectors of A will work for B and vice versa, because it need not be the case that an eigenvector of A necessarily is an eigenvector of B. For example, we could have something like A is the identity matrix, and B is any other diagonalizable matrix. So 5, negative 3, here's one we've done before. And so here, everything is an eigenvector of A, but the eigenvectors of B are along the lines y equals x and y equals negative x. So we can't just take any basis of A and of eigenvectors and say it's a basis of eigenvectors of B, but we certainly can find such a basis, and that, in this case, is something like that. Moreover, corollary 4.14 is almost enough to establish the following result about commuting linear maps H and K that are additionally self-adjoint. Now, if they're self-adjoint, we know they are diagonalizable. We proved that last lecture. And we also know that individually, we can find an orthonormal basis of X consisting of eigenvectors of H and of K. So we can find an orthonormal basis BH and another one BK consisting of eigenvectors of H and K. And by corollary 4.14, we can also find a common basis of eigenvectors of H and K, but it's not immediate why that common basis necessarily has to be orthonormal, or in other words, why we can necessarily find one that is orthonormal. It seems like it should be true, and so I said it's almost enough. It actually is enough. We can prove it, but it's not quite enough to immediately state this as a corollary. We have to do a little bit of work, and that work is really just understanding what a spectral resolution is. So that's the topic of the previous lecture. Please watch it if you have not. And this theorem, in the language of spectral resolutions, just says H and K have a common spectral resolution. And that is equivalent to what we were trying to prove about being simultaneously diagonalizable by an orthogonal matrix. In other words, having a common basis, orthonormal basis of eigenvectors. Formally, H and K having a common spectral resolution means that we have projection maps Pj of X onto common eigenspaces. So let's recall what that means. X we can break up as a direct sum of eigenspaces of H. So E lambda 1 all the way up to E lambda k. And so every vector x can be written uniquely as x1 up to xk, where h times xj equals lambda j xj. So these are literally the eigenspaces. And then the projection map pj just sends x to the jth eigenspace by sending x to this eigenvector xj. So that's the spectral resolution of H. And it's the way to really think about it is it's just a decomposition of X into the eigenspaces. And so I is the linear combination, is the sum of these linear maps. And H is just a linear combination of these projection maps. So it says we project onto each component independently, and then we stretch accordingly according to lambda. So having a common spectral resolution means that, so K is the linear combination of the same projection maps, but maybe with different scaling factors. So the lambdas are going to be the entries on the diagonal D sub A and the mu's on the diagonal matrix D sub B. So again, what this is saying is that we can write X, we can decompose X into a direct sum of eigenspaces that are eigenspaces of both H and K. And that's something that we know we can do because they are commuting. And then this, to fill in the gap from what I said almost, we also proved in the previous lecture that eigenspaces corresponding to distinct eigenvectors, eigenvalues, are orthogonal. So vectors, so these are not just, this is not just the direct sum of complementary subspaces. These are orthogonal complements. And that's the piece that is needed to conclude that they have a common spectral resolution. I'm not going to write up the details of a formal proof, but I encourage you to do it if you so choose. Now, let me finish with one more thing, just a sketch of how a direct proof from scratch of this result went. And you can also prove this entire thing from scratch too. It's not that bad. Let me do an example where maybe H it's maybe bigger than a 2x2 matrix, but it's got only two eigenvalues. So maybe X is equal to E1, the direct sum of E, or let me say E lambda 1 and E lambda 2. So because K commutes with H, this was the key idea. Because K commutes with H, that means that K restricted to either of these subspaces is invariant. So in other words, K sends E lambda J to E lambda J. So let me draw a picture of, let's suppose that the eigenspace suppose that the eigenspaces of H were like the xy plane. Maybe this is E lambda 1 and also the z-axis, so this is E lambda 2. Now K commutes with H, but what we know is K maps the xy plane to the xy plane. So H just takes the xy plane and it scales it by lambda 1. So it just blows it up maybe by 2 or by 3, whatever the eigenvalue is. But K is going to send this thing to normally how a linear map works. It sends square grids to parallelograms. And so I don't know, maybe restricted to this space, maybe this is one eigenvalue or vector. Maybe this is V1 and maybe this is V2. So then in that case, this is going to be one eigenspace, K eigenspace, and this is another one. So we can break this up into E, I don't know what notation to use, lambda 1, 1, direct sum with E lambda 2, 1. So this is maybe E lambda 1 comma 1, and maybe this is E lambda 1, so sorry, lambda 1 comma 2. And now X can be written, it is a direct sum of 3 eigenspaces. And these 3 things are all individually eigenspaces of H, and they are eigenspaces of K. So these 3 factors. Now these 2 things happen to correspond to the same eigenvalue of H. That's fine. We are not necessarily saying that all of these lambda j's and all of these mu j's are distinct. They certainly do not have to be. But that's how the proof of this thing went, is to use the spectral theorem and then further decompose them because K is invariant on each of the eigenspaces. Now I want to turn our attention to anti-self-adjoint maps. Remember what these mean. So A is anti-self-adjoint if A star equals negative A. And the key observation that we made in an earlier lecture is that if H is self-adjoint, then I times H is anti-self-adjoint. And that's because IH is IH bar transpose, which is I bar H conjugate transpose, which is negative I. Complex conjugate of I is negative I times H star. So why this is important is because if we have a linear map and we scale it, we multiply it by a scalar, we know how the eigenvalues and eigenvectors change. The eigenvectors don't change, and the eigenvalues change by that scalar as well. This means that if A is anti-self-adjoint, it's I times a self-adjoint map, so the eigenvalues of A are purely imaginary because the eigenvalues of H are real. Similarly, X has an orthonormal basis of eigenvectors of A because multiplying by a scalar, whether it's real or imaginary, doesn't actually change the eigenvectors. I'm bringing this up because this is yet another class of linear maps that we know have an orthonormal basis of eigenvectors. A question that I want to pose to you is which linear maps have orthonormal bases of eigenvectors? In other words, what condition or what property of the linear map is necessary and sufficient to ensure that there will be such a basis? Because orthonormal bases of eigenvectors is a really nice thing to have. We've already seen that self-adjoint linear maps and anti-self-adjoint linear maps all have orthonormal bases of eigenvectors. We've also seen that orthogonal maps and unitary maps all have this property as well. Remember, these things were just isometries, or rigid motions. Orthogonal is what we call them when we are in a real vector space and satisfies Q transpose Q equals the identity. And unitary maps is what we call them when we are over the complex numbers. So here, U conjugate transpose U is the identity. Remember that condition for these, a necessary and sufficient condition for this in matrix form was that the columns formed an orthonormal basis. All 4 of these families are actually a special case of a more general concept. And that is something called, and I apologize for this, a normal linear map. And I apologize because the word normal is used way too much in mathematics. We have normal vectors, we have normal subgroups, we have a lot of things that are just, the label normal is thrown on. And I don't think there is a unifying theme as to what normal really means. So it really should be called something else. But here's the definition. A linear map N is normal if it commutes with its adjoint. So if n star n equals n star. Notice that both of these products, n star and n star n, are self-adjoint. and hence they are normal themselves, because self-adjoint linear maps is a subfamily of this. Now, why are these normal? Well, it's easy to see. Take n star, take the adjoint, and you get n. So remember, you reverse the order of these and add a star. So n star star times n star, which is n times n star. So in other words, the adjoint of this one is that, and vice versa. And here's our theorem, 6.6, which says that if n is a normal linear map on X, then X has an orthonormal basis of eigenvectors of n. Now, a natural question is, what is so special about this property that's going to give us an orthonormal basis? And that's a good question, and it's not clear immediately from looking at it. But the reason why this holds is because any linear map n, normal or not, can be decomposed uniquely as a sum of a self-adjoint map and an anti-self-adjoint map, namely n plus n star over 2 and n minus n star over 2. I like to think of this for real valued matrices as writing a matrix as a sum of a symmetric and a skew-symmetric matrix. Okay, so what does that have to do with n being normal? Well, if n is normal, then these two linear maps, H and A, commute. In other words, this implies that HA equals AH. So what good is that? Well, so H is self-adjoint, A is anti-self-adjoint. Well, H is self-adjoint, but I times A is anti-self-adjoint. And so these will commute as well, clearly, because multiplying by a scalar doesn't change anything. And so by the theorem that we just proved, H and IH, and hence H and A, IA, have a common orthonormal basis of eigenvectors. So if H and A have a common orthonormal basis of eigenvectors, then so will their sum, which is n. Okay, so I'm not going to actually write out all the details in this proof. I think I've given you most of a sketch. So let me write a little bit more things I haven't done. So actually, this is not a, well, I haven't written an if and only if thing, but the converse of this will hold as well. And I think I'll leave that as a homework exercise. So let me sketch what I've basically said is, let's say that n is normal. So n star n equals n star. Then I claim that these two things commute. And let's check. So HA equals n plus n star over 2 times n minus n star over 2 equals 1/4 n plus n star times n minus n star. And this is, let's do it down here, 1/4 n squared minus n star squared plus n star n minus n star. So if n and n star commute, then these will cancel. And if they don't, well, it's easy to check that AH, I'm going to compare it up here, if we multiply these in the reverse order, then what's going to happen is the sign of these flip. So we will get 1/4 n star minus n squared times n star squared minus n star n plus n star. So if n is normal, then these two things commute. If it's not normal, they will not commute. So that's an if and only if thing. So again, if n is normal, then H and A are commuting linear maps, and so H and IA are commuting self-adjoint linear maps. Therefore, they have a common orthonormal basis of eigenvectors, and that's what we had to show. So once again, I claim that this theorem states the forward direction, but I claim that the converse holds as well. So this property of n commuting with its adjoint is precisely what is needed for there to be an orthonormal basis of eigenvectors. And to show that, I think it's easier to use the algebra, and that if there is an orthonormal basis of eigenvectors of m, then that means we can conjugate m, change bases, via a unitary matrix to get a diagonal matrix. So if we use that, we should be able to show that the converse holds, and I will leave that as homework. Let's move on and investigate what else we can prove about normal linear maps. Now, remember, you should think of these things as the linear maps that have an orthonormal basis of eigenvectors. That's a very special property, so it's not surprising that there's a lot we can prove about that family of maps. So I'll do a little bit in this lecture, and then I'll leave some more for the homework. So be sure to check that out. So here's proposition 6.7. The first part is more just of a lemma that we're going to need for the second part, and it holds for all linear maps. So if M is a linear map, then we certainly know that if the inner product of mx and y is equal to 0 for all x and for all y in x, then it must be true that mx is equal to 0. And since this is true for all x, that means for all x, and that means that M is the 0 map. Now, it's less true what we can deduce if just the inner product of mx with x is equal to 0. That it's not necessarily obvious that that implies that M is equal to 0, but I claim that it is. What if like M was some linear map that somehow took any vector and it sent it to something orthogonal to it? It seems believable that maybe there's a linear map that does that. But it turns out it's not the case. So let's actually prove that right now. And this is actually a little bit messy to do. And I'm going to leave a little bit, I'll show you how it goes. And I'll let you check some of the details. It's not hard. It's just notationally a little bit cumbersome. So let's take the inner product of mx and y for two arbitrary vectors. And if we can show that this is equal to 0, we're done by the comment that we made up here. So we can write this as, I claim, 1/4 times the inner product of mx plus y with x plus y minus the inner product of m times x minus y plus I times the inner product of mx plus iy, x plus iy, minus I times the inner product of m and x minus iy and x minus iy. Now, it's not obvious why this equals here, but it's also not difficult either. You just kind of follow your nose. You just do the rules. Let's see, 1/4. I'll simplify a little bit. So this is going to be mx plus my dot x plus y, and you could break that up into 4 parts, minus mx minus my dot x minus y plus I times mx plus I my x plus iy minus I times mx minus I my x minus I y. So at this point, it's believable that this is going to equal that. And it's also, again, there's nothing really too much to check. I mean, there's nothing too deep other than to just check that, you know, this is mx dot x plus mx dot y plus my dot x plus my dot y. That's this. That is this first thing here, and then I could just go through all this, but I don't think it's worth doing. I'm just gonna say check it yourself. Nothing too deep. This one's gonna hold. Okay, so why is part 2 true? So this is saying that an equivalent characterization of M being normal is that the image of any vector is the same norm under M and under its adjoint. That is perhaps a little bit surprising. So this is saying that M commutes with its adjoint if and only if these things stretch any vector the same amount. Okay, so let's prove that down here. So M being normal is the same thing as, I'm going to write this as M star M minus M star being equal to 0. So if this is the 0 map, then that is going to be the same thing as well, by part 1 here, by taking M star M minus M star, x dot x being equal to 0. So normally we have one direction. If this is true, then clearly the second part is true. But part 1 says this is an if and only if. The converse holds as well. Oh, and I should probably say, you know, obviously for all x in x. And now I think you can see what to do. And we just break this up using linearity, using bilinearity. So I can write this as M star M x dot x. I'm going to skip a step here. I'm going to move this. I'm going to move this to the right-hand side. This equals M star x dot x for all x in x. And now, notice what these things are. This thing here, we can move the M star over to the right-hand side, and this is equal to mx dot mx, which is equal to the norm of mx squared. And right here, this is, we can move the m to the right-hand side again and make this m star x dot m star x, and this is the norm of m star x quantity squared. And that's exactly what we had to prove, that these two conditions are equivalent. So this is a neat characterization of what it means to be normal. And an immediate corollary of this is that the null space of any normal linear map and its adjoint are the same. So this is a good time to mention that my previous notation of null space doesn't work well here because, you know, I've used NA to be the null space of A, and I really don't want to write things like N sub N. But I could still write a one-line proof of this. The null space of N is the set of all vectors in X such that one way to write it is the norm of NX equals 0. And by prop 6.7, this is the same set as the set of all vectors such that the norm of n star x equals 0. I want to conclude with a quick comment about unitary linear maps. Now these we know are normal because they satisfy U star U equals the identity. In other words, the adjoint is the inverse, and clearly those two things commute. Now these are isometries of complex inner product spaces, and that's when we first encountered them. And when we did, we proved that the determinant of U, which is a linear or a complex number, has norm 1. So in other words, it lies on the unit circle. And that should make sense. So it's e to the I theta. But we can actually conclude something stronger than this. So the determinant of U is just the product of the eigenvalues, lambda 1 up to lambda n. And I claim that all of these eigenvalues have norm 1. So if they all have norm 1, then their product has norm 1 as well. So proposition 6.9 says that if U is unitary, well then first of all, X has an orthonormal basis of eigenvectors. That's because it's normal. And each eigenvalue has norm 1. So this is in some sense a way to characterize what the unitary maps are. So you can picture in your mind, you have this orthonormal basis. So this is C3 complex space. You can't really visualize this, but you get the idea. And what U is doing, U is some lambda 1 P1 plus lambda 2 P2 plus lambda 3 P3, where P1 and P2 and P3 are projections onto these eigenspaces, and lambda 1, lambda 2, and lambda 3 are the complex eigenvalues, and all of them have norm 1. Now, something that we will get to probably in the next series of lectures is what's called the polar form of a linear map, and it involves decomposing any linear map into a unitary linear map and a positive semi-definite map. And I won't say too much about that, but you can think of it as how any complex number can be written as some radius times e to the I theta, and this is just a rotation. So it's a point in the unit circle scaled by r. And later we will see how any linear map M can be written as a unitary matrix. So you can think of this as a rigid motion, like a rotation and or reflections in complex inner product space, times a positive semi-definite matrix P. That just means all of the eigenvalues are non-negative. And P turns out to be the square root of M star M. Now, we haven't talked about what the square root of a matrix is, but I'll give you a quick preview. You'll see it on your homework. That really the proper way to square a matrix is not M squared, but M star M, because this guarantees that the eigenvalues are going to be real valued. And if you have that, then the eigenvalues, well, then it's going to be similar to a diagonal matrix lambda 1 bar, lambda 2, I should say, squared, lambda n norm squared, where z norm z squared is z times z bar. And so if you have a diagonal matrix like this, it makes sense to talk about the square root of this matrix, and that's really the square root of the linear map with respect to the diagonal or the eigenvector basis. And so the square root of the square is in some sense a linear map that is going to scale everything along the eigenvectors, and then U is going to be some rigid motion that orients it properly. So this is just a bit of a preview. More on this later in the next section when we talk about positive definite matrices and singular value decomposition. And I think we're going to leave things there. Stick around next time for a discussion on the Rayleigh quotient of a self-adjoint map, which is a way to derive the spectral resolution without appealing to the whole spectral theorem and the fundamental theorem of algebra. It also gives us some neat results of self-adjoint maps, like something called the min-max principle or characterization of eigenvalues. And it's also very relevant to numerical linear algebra. So stay with us.